Section: Introduction. In this section, we explore the capabilities of large language models, LLMs, in understanding symbolic graphics programs. Recent research indicates that LLMs can generate basic computer programs, suggesting they have some grasp of program structures. We shift our focus to symbolic graphics programs, which create visual content like images or 3D assets through programming. Our main question is whether LLMs can truly understand these symbolic graphics programs. To clarify what we mean by understanding, we define it in terms of how well LLMs can comprehend the images produced by these programs. We assess this understanding by evaluating their ability to answer semantic questions based solely on the program input. These questions are designed to be straightforward when looking at the image but challenging when only considering the program text. We propose a framework for creating benchmarks to evaluate ILM's understanding of symbolic graphics programs with minimal human input. While we acknowledge that human understanding involves more complex visual reasoning, our benchmark aims to shed light on one aspect of understanding in LLMs. Understanding symbolic graphics programs is intriguing for several reasons. First, it may require LLMs to have a form of visual imagination, allowing them to visualize the graphics content. If an LLM can accurately answer all semantic questions about a program, we might conclude it has a strong visual imagination. Second, since symbolic programs generate graphics procedurally, understanding them involves long-range reasoning about the sequence of operations, which can significantly alter their meaning. Third, many questions require precise identification of semantic components, demanding a detailed understanding of the program structure. This leads us to investigate whether LLMs can semantically understand symbolic graphics programs and how we might enhance this ability. Answering semantic questions about these programs requires various sophisticated reasoning skills, making it an ideal benchmark for assessing ILM's overall reasoning capabilities. From a cognitive standpoint, it remains an open question how well LLMs can navigate such complex representations. To address the importance of understanding symbolic graphics programs, we developed a benchmark called SGP Bench, focusing on two types: scalable vector graphics, SVG, for 2D vector graphics, and customized computer-aided design, CAD, for 2D, 3D objects. Our benchmark includes two evaluation types. 1. Semantic understanding. We create multiple-choice questions based on a set of images from various categories and present these to LLMs alongside the symbolic program to assess their understanding. 2. Semantic consistency. We test the robustness of ILM's understanding by randomly altering the original symbolic programs and then asking the same questions based on these modified programs. This helps ensure that the answers remain consistent and reduces the risk of test data leakage. We also validate our automated labels through a human study. In addition to evaluating LLMs in a standard setting without fine-tuning, we investigate whether fine-tuning on a curated dataset can enhance performance. We introduce a new method called Symbolic Instruction Tuning, SIT, to improve ILM's understanding of symbolic programs. This involves collecting an instruction-following dataset based on rendered images, leveraging a powerful language vision model for detailed captioning and question answering. Our experiments show that SIT can indeed enhance an LLM's semantic understanding of symbolic programs. We are eager to pursue further research to improve this aspect of understanding. Our contributions include introducing the task of symbolic graphics program understanding and a scalable benchmark creation pipeline, developing SGP Bench for evaluating ILM's semantic understanding and consistency with SVG and CAD programs, collecting an instruction-following dataset and proposing SIT for better understanding of symbolic programs, creating a symbolic MNIST dataset, where understanding the symbolic problems is particularly challenging, revealing that ILM's comprehension differs significantly from human understanding, demonstrating that SIT can also enhance general instruction following performance. Section Summary. In this section, we explore the capabilities of large language models, LLMs, in understanding symbolic graphics programs, defining understanding, as the ability to answer semantic questions based on rendered images from these programs. We introduce SGP Bench, a benchmark for evaluating ILM's semantic understanding and consistency with symbolic graphics programs, and propose a new fine-tuning method, Symbolic Instruction Tuning, SIT, to enhance this understanding through a curated instruction following dataset. Section: Related Work. In this section, we discuss related work in symbolic graphics programs. Generating visual data through procedural modeling with symbolic programs has been crucial in computer graphics, especially for 2D shapes and 3D geometry. These programs provide a clear and structured way to represent graphics, which has garnered significant interest in the field. Common types of programs include constructive solid geometry, computer-aided design, vector graphics like SVG, L systems, and specialized domains. SVGs, made from basic shapes such as vector paths and polygons defined by mathematical equations, are particularly popular in artistic applications like icon design and typography. The vector path in SVGs allows for precise control over graphics, including shapes like rectangles and ellipses. In 3D modeling, especially in CAD, we use parameterized operations that can be modified and reapplied to create updated geometries. Datasets like the ABC dataset and Fusion 360 Gallery support CAD research and machine learning by providing structured information about models. Our paper focuses on understanding graphics programs in SVG and CAD by introducing a new task that requires complex reasoning with these programs. We explore how graphics programs can offer compact and scalable descriptions compared to raw pixel data, and we have seen efforts to derive graphics programs from 2D images, 3D objects, and scenes captured from multiple views. Some research has even looked into using graphics programs for visual question answering. Recently, advancements have been made in using large language models, LLMs, to generate graphics programs that can reconstruct visual inputs. In our work, we benchmark LLMs for semantic-level question answering, similar to visual question answering, but we use graphics programs as input without any visual elements. LLMs have shown great potential across various applications, including programming tasks like code retrieval and automated testing. Our research investigates how well LLMs can understand symbolic graphics programs, which is different from previous studies since the meaning of these programs is often visually defined. There are many benchmarks for evaluating LLMs in areas like AI safety and program understanding, but we focus on how well LLMs can understand graphics programs, which can be rendered into images. To assess model performance, we utilize various public multimodal datasets, including those for image caption pairs and visual question answering. Some recent datasets aim to provide more unified evaluation methods. We introduce the task of semantic understanding of symbolic graphics programs, aiming to evaluate how well an LLM can understand a symbolic graphics program, hinting at its ability to visually imagine. We leverage the link between deterministic symbolic graphics programs and their rendered images, assessing understanding through question answering performance. We use the same questions and corresponding symbolic graphics programs to evaluate ILM's understanding, without using the rendered images. Our evaluation suggests that if an LLM comprehends the symbolic graphics and can infer the rendered image, it should be able to answer semantic questions about that image. This understanding can also be seen as a form of visual question answering, where the visual input is represented by a symbolic program. Unlike existing models that encode images with text-aligned neural networks, we focus on symbolic programs that can accurately represent the graphics content, aiming to explore the potential of symbolic programs for visual reasoning. Section Summary. In this section, we explore the significance of symbolic graphics programs, such as SVG and CAD, in computer graphics and introduce a new task for assessing large language models, LLMs, semantic understanding of these programs through question answering, leveraging their correspondence with rendered images. We also highlight the development of SGP Bench, a benchmark specifically designed to evaluate ILM's capabilities in understanding symbolic graphics programs, distinguishing our approach from traditional vision language models. Section: SGP Bench. a benchmark for symbolic graphics program understanding. In this section, we describe our process for creating the SGP Bench benchmark, which involves generating questions about symbolic programs based on their rendered images. To efficiently gather a large number of questions with minimal human effort, we utilize a strong vision language model, like GPT-4o, to automatically generate semantic questions from the images. We then manually review these questions to ensure they are sensible and have correct answers. We also conducted a human study with a random selection of 500 generated questions and images, finding a high level of agreement among reviewers. Our dataset creation process, illustrated in a figure, includes rendering symbolic programs and querying GPT-4o, both of which are scalable and require little human input. Human annotators check the generated question-answer pairs, which is much less labor-intensive than creating them from scratch. We highlight that this method for creating program question-answer sets is broadly applicable to most symbolic graphics programs. For SVG and 2D CAD programs, we can directly produce 2D images, making the process straightforward. For 3D CAD programs, we first render 3D models into 2D images from fixed camera angles, then combine these images to query GPT-4o, following the same steps as with SVG. Regarding our dataset statistics, we collected a total of 1,085 SVG programs across 19 categories, each accompanied by 4 semantic multiple-choice questions with 4 answer options. We ensured that the answers were evenly distributed among the options. Our SVG benchmark includes 5 question types: semantic, color, shape, count, and reasoning, with varying numbers of questions for each type. Semantic questions assess the overall meaning of the SVG code, while the others focus on specific details like color, shape, and counting occurrences of patterns. For the CAD dataset, we gathered 2,400 programs from 3 sources, including 1,000 from DeepCAD for the 3D subset, 700 from the Fusion 360 reconstruction dataset for the 3Dracon subset, and 700 for the 2D subset. Depending on the dataset, we either render 1 or 2 images from opposite views and generate 1 semantic multiple-choice question and answer for each image, ensuring a balanced distribution of correct answers. In our experimental results, we found that understanding graphics programs is quite challenging. The average accuracy of all models, both proprietary and open source, was below 65% for SVG and below 80% for CAD. SVG posed a greater challenge due to its richer semantics. However, we observed significant performance improvements in line with the scaling law, with larger models showing better results. For instance, LLAMA3 improved its score on SVG as its size increased, and similar trends were noted for other models. We also noticed consistent improvements across different generations of the same model size and family. This suggests that understanding symbolic graphics programs is a fundamental capability that aligns with the scaling law of large language models, even if they weren't specifically trained for this task. Proprietary models, like those from the GPT family, generally outperformed the open-source models we examined. Notably, we saw a 27% performance boost from GPT 3.5 to GPT 4 on our benchmark. The best-performing model for both SVG and CAD was Claude 3.5 Sonnet. Our benchmark allows for probing the semantic understanding of graphics programs across various aspects, from specific attributes like color and shape to broader concepts like semantics and reasoning. Most models performed well on color questions, followed by shape, with counting and semantic questions showing lower accuracy. This pattern reflects the structure of visual information processing, where color is the most prominent feature, and understanding shape requires more nuanced comprehension. Open-source models struggled with semantic questions, while GPT models performed relatively well, making semantics their second-best category after color grounding. Section Summary. In this section, we describe our dataset creation pipeline for SGP Bench, which utilizes a vision language model to generate and validate semantic questions from rendered images of symbolic programs, significantly reducing human effort. We present statistics from our SVG and CAD datasets, highlighting the challenges in understanding graphics programs, with performance improvements observed in larger models, particularly among proprietary models like GPT-4, which outperform open-source counterparts. Section: Benchmarking Semantic Consistency. In this section, we explore the semantic consistency of large language models, LLMs, when exposed to various transformations of SVG graphics. We utilize a semantic consistency test that involves applying global translations or rotations to SVG images, which allows us to maintain the essential characteristics of the graphics while altering the underlying code. This approach helps us determine if the ILM's understanding is based on genuine comprehension rather than mere memorization. We use our SVG dataset to assess how well LLMs handle these transformations. For each SVG sample, we randomly select 5 different translations and rotations, resulting in minimal visual changes but significant alterations in the SVG code. We then evaluate the LLMs using the same set of questions from the SVG understanding benchmark, but with these modified inputs. To measure semantic consistency, we employ 2 metrics: the average accuracy of the ILM's responses to the altered SVG inputs and a consistency score that reflects how often the models provide the same answer across different perturbations. A score close to 1 indicates high consistency, regardless of the changes in the input code. Our experiments reveal that most LLMs demonstrate strong semantic understanding, achieving over 80% consistency in their predictions under both types of perturbations. This suggests that their ability to understand graphics programs is likely not due to data leakage but rather a fundamental capability to interpret symbolic graphics. Next, we assess the prediction entropy of various LLMs and compare it to human responses. We find that humans show strong agreement when answering questions based on rendered images, while LLMs exhibit lower consensus, indicating different mechanisms at play in their understanding of symbolic programs. To enhance ILM's understanding of symbolic programs, we introduce a method for symbolic instruction tuning. We create a dataset of semantic descriptions for symbolic graphics programs by rendering them into images and using a powerful vision language model to generate detailed captions. This dataset contains descriptions for 55,000 symbolic programs. We then fine-tune open-source LLMs using this instruction data, following standard procedures. Our results show that this approach significantly improves the understanding of symbolic graphics programs, with Llama-3.1-8b's performance increasing from 46.7% to 51.4%. While we achieve competitive results, we recognize that further challenges remain in enhancing the performance of open-source LLMs beyond that of GPT-4o, which served as the source for our instruction data. Section Summary. In this section, we propose a semantic consistency test for large language models, LLMs, by applying global translations and rotations to SVG graphics, which alters the code representation while preserving semantics. Our experiments show that most LLMs maintain high consistency in their predictions despite these perturbations, suggesting a robust semantic understanding rather than mere memorization. And we also introduce symbolic instruction tuning to enhance ILM's comprehension of symbolic graphics programs. Section: A challenge for SVG program understanding. In this section, we explore the challenge of understanding SVG programs and whether it is truly easy to answer semantic reasoning questions about them. We conducted an interesting experiment that shows SVG programs can be quite tough for large language models, LLMs, to grasp, even when the images they create are simple for humans to recognize. Despite their power, these LLMs often perform at chance-level accuracy. We designed symbolic graphics programs that generate images similar to those in the MNIST dataset. These programs are relatively straightforward, usually involving just 1 or 2 path operations. We introduced the SGP MNIST challenge, which includes 100 symbolic graphics programs for each digit from 0 to 9, totaling 1,000 programs. For each program, we posed a multiple-choice question asking which digit the SVG program represents. The results revealed that, while humans can easily identify the rendered images, LLMs struggle with the corresponding symbolic programs. Even the advanced GPT-4o model only achieved slightly better than chance-level accuracy. This indicates that understanding symbolic graphics programs is generally challenging for LLMs, highlighting a significant difference between how machines and humans interpret images. Recognizing these differences is crucial for developing systems that can effectively collaborate with us. We believe our benchmark can pave the way for better understanding of symbolic graphics by LLMs. Next, we examined how to enhance instruction tuning with symbolic graphics programs. We tested instruction-tuned models across various popular benchmarks that assess language understanding, generic reasoning, and mathematical problem-solving. We started with the Llama-3.1-8b base model, which we fine-tuned using the OpenInstruct dataset containing 143,000 question-answer pairs. We evaluated the impact of incorporating our Symbolic Instruction Tuning (SIT) data into the OpenInstruct dataset. Additionally, we explored a reverse approach, where we rephrased answers as questions and vice versa. We tested 3 methods for using SIT data: mixing original SIT data with OpenInstruct data, mixing reverse SIT data, and combining both types. The results showed that integrating SIT data generally enhances the ability to follow instructions, suggesting that understanding symbolic graphics programs requires various reasoning skills. Notably, using reverse SIT data for generating symbolic graphics programs improved reasoning abilities that complement understanding these programs. The combination of both original and reverse SIT data significantly boosted the instruction following capabilities of LLMs, outperforming the baseline models. In conclusion, we propose a new evaluation task for LLMs focused on understanding images directly from graphics programs, without visual input. We created SGP Bench, a benchmark that highlights differences in LLM performance, and introduced the SIT method to enhance their understanding of graphics programs. Our work aims to deepen our collective understanding of LLM capabilities and inspire a wider range of evaluation tasks. However, this is just the beginning of exploring symbolic graphics program understanding in LLMs, and further investigation into the mechanisms behind this semantic understanding is still needed. Section Summary. In this section, we demonstrate that understanding SVG programs is challenging for large language models, LLMs, as evidenced by our SGP MNIST challenge, where even advanced models like GPT-4o achieve only chance-level accuracy despite the rendered images being easily recognizable by humans. We also introduce Symbolic Instruction Fine-Tuning, SIT, to enhance ILM's capabilities in understanding graphics programs, revealing that a combination of original and reverse SIT data significantly improves their instruction following abilities. Section: Acknowledgement. In this section, we express our gratitude to Yao Feng and Yandong Wen for their valuable suggestions. We also want to thank Hanqi Zhou for her support throughout the project, during which we got engaged. Fun fact: we married just hours before the submission deadline. The diamond ring in the figure represents this happy occasion and is a gift from our entire team. Our work received partial support from the German Federal Ministry of Education and Research through the Tübingen AI Center and the Machine Learning Cluster of Excellence. One of our team members, WL, was supported by the German Research Foundation for a project on robust vision. KMC received support from the Marshall Scholarship and Cambridge Trust, while A was funded by a Turing AI Fellowship and the Leverhulme Trust. MJB has also received research funds from several companies and has financial interests in others, but his work on this project was conducted solely at the Max Planck Society.